Manshi, you're able to see my screen, right?
Yes, ma'am.
Okay, okay, fine. Fine. Okay. So I welcome you for the week 9 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. So let's have a brief recap of the lectures of week 9. Manshi, were you able to go through the lectures of week 9? Once again, I think you might have typed in chat. Sorry, 1 second. Hold on. Just come to the screen. Were you able to go through the lectures? Okay, I think there's no response. Are you there, Manshi? Okay, okay. Okay, let's proceed with the brief recap of the lectures. Okay, so week 9 had 9 lectures. Sorry, 8 lectures, and it had two different set of lectures. One was on interaction of polymers with other materials. The second set of lectures were on polymer processing. Okay, so the interaction of polymers with other materials. The lecture on this started with lecture 62. This was in continuation with previous week's set of lectures, which was again on interaction of polymers with other materials. The lecture 62 was on compatibilizers. Okay, so compatibilizers uh, for blends. So what is the role of compatibilizer? For example, it helps in increasing the interfacial strength and dispersion of the blends. Was discussed, and then how do they actually increase the interface region uh, was discussed. For example, if you have an immiscible blend, the thickness of the immiscible blend is 2 nanometer, and when there is an action of the compatibilizer, what happens is that this interface thickness it increases. That means there is more of this a coalesced region, sorry, not a coalesced region, a region having a uh, both the polymers like, hello, anything you wanted to say, Manshi? Shall I proceed?
Yes, ma'am.
Okay, okay. So how do they, help in, increasing the interfacial region? So there is a gradual transition. Instead of, having, a pure region of polymer 1 and polymer 2 in the blend, there will be a gradual transition. I mean, there will be a interface region where there will be, good mix of this, polymer 1 and polymer 2. So this is what, the compatibilizer plays a critical role in. So this kind of compatibilizers, they can be of two types. One, they'll be reactive, and the other is a non-reactive. In case of non-reactive compatibilizer, some examples includes the graft and copolymers. They can act as a compatibilizers, or a core shell impact modifier. So there will be some core and a shell. So this shell will help in connecting, the polymers, two different polymers. So that will be, acting as a compatibilizer. In case of reactive compatibilization, there will be some N groups, which can react with the backbone of the second polymer. So in this way, there is a compatibilization or blending or better blend formed between the two polymers, or there can be some cross-linking reaction that is happening. Okay, or there can be some ionic bonds that can be formed by these compatibilizers. So these are some of the examples of the reactive compatibilizers that were discussed in the lecture. The next was on fiber treatment and sizing. Okay, what are the surface treatments, like use of a coupling agent or a film former was discussed. And then, what are the components for sizing of glass fibers were discussed. And the role of sizing in glass fibers was discussed. The next was on natural fibers and polymers. Cellulosic hydrophilic fibers and the hydrophobic polymers. You know, the interactions. What kind of treatments can be done. To have a better interaction between the cellulosic hydrophilic fibers and a hydrophobic polymer. So, for example, there can be some physical treatment that are being done. For example, change in surface roughness can be done through plasma treatment, or there can be some chemical treatments also. For example, use of silane isocyanate or use of some graph polymers, or there can be some alkali treatment that that can be done in order to have a a better interaction between the cellulosic hydrophilic fibers and hydrophobic polymers. So this was discussed. And the next part of discussion was on how compatibilizers and sizing of these fibers play a very important role when you want to recycle a mixed plastic waste. Okay. This was discussed on that. There was a discussion on that. The next lecture was on.
Okay, ma'am.
Okay. Shall I proceed? Okay. I'll just proceed. The next lecture was on biopolymer application. Here actually two different biopolymers were discussed. One was xanthan gum. Do you remember, what is the source of this xanthan gum? How is xanthan gum produced? It was discussed in one set of previous lectures. Do you remember what is it? From where do you get this xanthan gum? Okay. So it is it is produced from a bacterial origin. Okay, from Xanthomonas species. Okay, and this xanthan gum has different types of interactions because this xanthan gum basically has OH and COOH groups in it, and this leads to variety of interactions. So it can be intermolecular and intramolecular interactions also, and there can be ionic interaction also because you have this COH group, so you can form CO minus anion. Okay, so this kind of ionic interaction can also take place. And this xanthan gum, it is used as a thickener in wide variety of application. For example, the toothpaste you use will have some xanthan gum, and puddings, ice creams may have xanthan gums also as a thickener. And one other application, it is in enhanced oil recovery. Okay, and the xanthan gum, it can have different molecular conformation based on its state also. Okay, for example, in solid state it will have a different kind of conformation. Okay, and when it comes to solution state, again due to different interactions and ionic strength or temperature, there can be different conformation that is possible in case of xanthan gum. For example, low ionic strength or high temperature can lead to a random coil conformation, whereas a high ionic strength or low temperature can lead to a relatively rigid and helical rod kind of conformations. Okay, and when it comes to xanthan gum, a lot of interactions plays a very vital role when it is used as a viscosity modifier. As I said, there can be intramolecular as well as intermolecular interactions, and there can be polymer and solvent interactions. Okay, and so these kind of interactions, it plays a very critical role in its application. Okay, the next example that was discussed in this lecture was on uh, polyisoprene. Do you know what is polyisoprene? One of the natural sources of natural rubber. Okay, so the next discussion on the natural biopolymer was on natural rubber. Here, so we saw in xanthan gum that the interactions like hydrogen bonding or an ionic interaction, it plays a vital role in its different conformations and all. whether it is in solid state or in solution state. Okay, whereas in case of polyisoprene, you know that natural rubber, it is used as an elastomer, correct? It is used as an elastomer, and it is also used as a in damping applications in vibration mount, correct? Yes. So here it is not the interactions between the polymer molecules, but it is the role of the segments that plays a vital role. Okay. How does it play a vital role? Do we have any idea? So when it is going to be used as a elastomer, what happens is that the segments get stretched, and then when when you're stretching the, for example, your rubber band, the segments get stretched. Okay, and when you leave it, it recoils and comes back to the original position. Okay, so this is how the elastomeric behavior of rubber happens. Okay, and this is how it is used in elastomeric application. Whereas in case of vibration mount, here again, the segments play an important role. Okay, how do they play an important role? Here what happens is that the segments does not get stretched, but what happens is that the segments does not get stretched, but what happens is that these segments take different conformations depending on the vibration. So the vibration it receives, it causes the change in conformation, and this is how the mechanical energy of vibration is dissipated as heat, and thus it acts as a vibration mount. So you could see a complete contrast between a xanthan gum where interactions like your hydrogen bonding or your ionic interaction plays critical role, whereas in case of a rubber, the segmental motion, it really plays a very vital role in its application. And in fact, rubber is a classic example of ideal system. Ideal system you could actually correlate to an ideal gas, right? So there is no molecular interaction in case of ideal gas. Similarly, in ideal system also there is no molecular interaction. Here again, it is these segments that are playing a very vital role, right? So two different extremes of interactions where there is a lot of interactions that is happening, and when there is no interaction but it is more of a segmental motion that is playing a vital role in two different polymers were discussed in this lecture. Okay, and then the next lecture was on adhesives and paints. So adhesives, do you know what are adhesives? So adhesives helps in joining two dissimilar materials. So, for example, you can paste a paper on your, cupboard using an adhesive, correct? Or you can, join two metals, or you can join a metal and a ceramic using adhesives. Okay, so these are some of the, examples, where adhesives can be used for joining different materials. And these adhesives can be of different types. They can be structural adhesives. When it comes to structural adhesives, what is meant by structural adhesives? So here it means that it plays a structural a role, that is it plays a role in load bearing. So when it is going to play a role in load bearing, the adhesive strength should be very good. So this was discussed in the lecture. And then what are the mechanisms of adhesions, and then what are the different so other types of adhesives like flexible adhesives, sealants. When it is going to act as a sealant, so it should avoid leakage of any solvent or any fluid passing through it, right? So this was discussed, and what are the different types of adhesive failures was discussed, and what are the different types of adhesive formulations. Okay, and what are the mechanisms of adhesion? Like the mechanism of adhesion can be through mechanical bonding, or through secondary interactions like van der Waals interaction or hydrogen bonding, or it can be through chemical adhesion. Okay, where a reaction happens between the adhesive and the surface on which it is applied. Okay, and what are the different adhesive formulations were discussed? For example, pressure adhesive, sensitive adhesive. Do you know one classic example of this pressure sensitive adhesive, where you just apply a pressure and then it gets you can paste it. For example, in your sticky note you use a pressure sensitive adhesive. So you would have used a sticky note, right? In your books, or for something to remember, you would have pasted in your shelf or somewhere. You want to do this or that. So it has that adhesive, which is pressure sensitive. So when you just apply a pressure, it just the adhesive present in it just gets stuck to it. Okay, this is one example of the adhesives. The next material that was discussed was paints. Paint, it is nothing but again it is an example of an adhesive only. Okay, the difference is that it actually adheres to one side of this, on one side it adheres to the surface, and on the other side what it does is that it can either play a role of just aesthetic, adding aesthetics. For example, paints can carry pigments. Okay, so that gives, you can have different colors, so that will give aesthetic pleasing effects. Or it can act as it can act as a coating also. Like what happens is that you can have some anti-corrosive coating. Okay, or scratch proof coating, or a UV coating, right? So and polymers play a vital role in this, paints. Okay, they actually carry the pigments and other additives, and also they can have their own application perspectives also. Okay, so the role of polymers was discussed. So it helps in binding pigment particles. Okay, and it actually adheres to the surface. And the next important aspect that was discussed was the rheological response of paint. So when it comes to paint, so when you apply it, it has to flow, correct? It has to flow very easily, right? You should be able to apply the paint very easily. Whereas once it is, once the painting is done, it shouldn't drip. It should get, you know, yes, it should be smooth to apply, perfect. And once it is applied, it should be, it should get, adhere to the surface, and it should not drip. Correct. So the rheology plays very important role in, in case of paints. So this aspect was discussed, and then there was a discussion on water-based paints, which are associative thickeners. Okay. The next lecture was on dissolution and recovery. Okay. From this lecture onwards, the concepts was on polymer processing and recycling. Okay. So, uh, this lecture 65 was on dissolution and recovery, and this was on sustainability aspect of the course. Okay. So here in this, lecture, uh, the polymer recycling operation, especially the challenges involved in mechanical recycling process. Okay, what do you think some of the challenges that will happen, in case of a mechanical recycling? For example, you have a, polymer, you start mechanical recycling, just keep on recycling it, just so what happens? So there are several challenges that are involved in case of a mechanical recycling. One of them is the degradation of polymers during its service life. So what happens is that during the service life itself, the polymer starts degrading. So there can be some oxidation possible. Okay, there can be some change scission possible. So the mechanical strength of the original polymer and your recycled polymer might not be same. Okay, so these are some of the challenges involved in mechanical recycling. So in what other way you can recycle polymers? So it can be, and eliminate polymer waste. It is chemical recycling process. So in chemical recycling process, you have different types of recycling process. You can just combust the material, right? In this way, what happens in case of combustion? You're just converting a polymer waste or some waste into carbon dioxide and hydrogen. But this actually eliminates the waste, but you should also think of the carbon dioxide equivalent emission. So carbon dioxide equivalent emission of different chemical recycling process was discussed. So different chemical recycling processes include combustion. So combustion, as we discussed, it is just burning the waste and bringing in, and you will get carbon dioxide and water. So the combustion can also be merged with the energy production process also. Okay, and also there can be pyrolysis process that can happen. In pyrolysis, what happens? You end up with a material which is having fuel like characteristics or petrol like characteristics. There can be gasification. The other chemical recycling operation is dissolution, where you dissolve the polymer into a solvent, okay, and then reprecipitate it, okay. And among different chemical recycling process, this dissolution process has a very low carbon dioxide equivalent emission index. Okay, that that is very important in terms of sustainability aspect of it. Okay, so what happens, when your macromolecule is recycled through dissolution? So you will have in this dissolution process, you will have solvents and anti-solvents. Solvents, it helps in dissolving the polymer. Okay, you have mix of polymers and polymeric waste. It will have some combination of polymers. It may have some combination of polymer blends or copolymers or polymer composites or everything. So you're trying to dissolve it in solvent. So the solvent dissolves the polymer alone, and once it dissolves, so it is in solution phase. Now you have to take it back so that you get the pure polymer. So for that you may use some anti-solvents, right? And also again, when you are using a solvent, there is again an sustainability aspect, right? What about the recovery of solvent, or you are using some organic solvents? For example, when you want to recover HDPE or LDPE or polypropylene, some of the common solvents used are toluene acetone, xylene, and hexane. So these are all organic solvents. Again, when you are having organic solvents, they'll have environmental impact, like they may be carcinogenic. Okay, so this is again point of concern. So what kind of research are going on is that use of alternate solvents, like using of ionic liquids or plant based green solvents or some supercritical fluids are used. Okay, and when it comes to dissolution of polymers, the dissolution rate is generally low. Why is it low in case of polymers? Why do you think dissolution of polymers is slow? Any thoughts? Because of the macromolecular nature itself, the resolution rate is very slow. So, because of the macromolecular nature, first of all, the solvent has to dissolve through this macromolecule, right? The solvent molecules are small molecules, so they have to dissolve through this. So, and then it has to cause segmental relaxation, and it has to cause disentanglement of the polymer. Okay. For example, when you think of dissolving an amorphous polymer, okay, for example, an amorphous polymer is exposed to solvent. This amorphous polymer exposed to solvent will have different layer. For example, in the first layer, what will be there is a liquid layer. This will have large amount of polymer which is already which is dissolved in the solvent. The next layer, since the your solvent molecule can diffuse little by little only, the next layer will be a gel-like layer, with entangled polymer and a large amount of solvent it will have. Okay, further going down into the polymer structure, the next layer will have much lesser of solvent, but it would have caused some, it would have, plasticized the polymer. So it would have become more rubber-like in this layer. Okay, with a large amount of segmental mobility. And the final layer, it might have, very glassy, layer. Okay, where the solvent has not yet diffused. Okay, and when you think about, sorry, when you think of the diffusion process, it is not a Fickian diffusion process, right? In your diffusion flux, in case of Fickian diffusion, your diffusion flux is proportional to your concentration gradient, right? That is a fixed law of diffusion, right? And your constant of proportionality is your diffusion coefficient or diffusivity, right? And this diffusivity is a constant value, right, for a particular system. Whereas in case of non-Fickian diffusion, this diffusivity is not a constant, but it is a function of concentration itself. Okay, so in case of polymers, this kind of non-Fickian diffusion or anomalous diffusion happens. Okay, these were all discussed in the lecture 65, dissolution and recovery. Okay, the next lecture was on polymerization kinetics. So different polymerization operations were discussed. So what polymer manufacture, and what are the polymer processing operations, like your extrusion, moldings operations were discussed. And then your reactive processing, and for example your reaction injection molding. In case of reaction injection molding, what happens is that there is a polymerization process happening, as well as a shaping operation happening. And what are the aspects of composite processing? Okay. For example, in case of composite processing, what happens is that for you the one of the type of process that can happen is that in case of thermosets, especially thermosets with reinforcement, you will have a premix or a resin, and this resin is mixed with a reinforcement, and then you form a pre-preg or compound, and then this is frozen. Why is it frozen and stored? To avoid cross-linking operation. Okay. So uh, after this pre-preg is formed, then it is actually taken for final molding operation. So during this, the shaping happens. Okay, whatever desired shape you want happens, and then finally cross-linking reaction happens. This happens. And then the next discussion on this lecture was on kinetics of different polymerization. For example, free radical polymerization, strep growth polymerization, and living polymerization. The kinetics of each of these polymerization operations were discussed. Okay, you are able to follow, right? Manshi, are you there? Okay. Okay, now let's proceed. Yeah, in the next lecture, it was on polymerization reactors. So the mode of polymerization. So what are the industrial polymerization operations? You have bulk polymerization, okay, and then solution polymerization, precipitation, suspension, emulsion polymerization, and gas phase polymerization. So the advantages and the key aspects of each of these polymerization processes were discussed in detail. Okay, and and then what are the industrial polymerization operation for some classic examples of polymers like your HDPE, LDPE, and polystyrene were and some other examples were also discussed. Okay. The next lecture was on polymer processing. So here, what are the different you know unit operations involved in polymer processing? For example, you will have a mixing operation, plasticization operation. Okay, where some additive to plasticize the polymers. For example, a homopolymer. In order to plasticize a homopolymer, for example, a polypropylene, you will add a plasticizer. So that was discussed. And then your melting operation, reactions, and what are the shaping operations, like you mold it or stretch it or pass it through rolls. Okay. And the solidification process. So these aspects were discussed. Okay, what are the different polymerization process, sorry, polymer processing techniques? Like you have different polymer processing techniques includes extrusion, injection molding, compression molding, film blowing, and then blow molding, coating and calendering, where the polymer is passed through rollers. Okay, and roll mill, rotation molding, thermoforming. So these were some of the polymerization techniques that were discussed in brief in that lecture. Okay, and then there was a discussion on melt flow index measurement. Okay, and the flow behavior. Uh, for example, in case of polymers, you do not have a Newtonian behavior. It will be non-Newtonian behavior. So, how is the stress and shear rate related? And what are the dimensionless numbers in polymer processing operations? You have Deborah number, Wiesenberg number, Reynolds number, and elasticity number. So, these were all discussed in, polymer processing 1. And the final lecture for the week was on polymer processing 2. Here, two polymer processing operation. One was extrusion that was discussed in detail, uh, where there was a detailed explanation on single screw extruder and extruder characteristics, the extruder variable, die opening, the pressure drop were discussed. And then injection molding operation. How does the injection molding operation happens? What is the processing window in which you get a good product in case of injection molding? Okay. And how do you analyze the processing operation? For example, what is the idealized flow? How do you there should be some set points, right? You will have some set points in order to understand the flow behavior in case of polymer processing, because obviously in polymer processing there will be some flow happening, right? It has to pass through some extruder, right? It has to pass through some roller. So in each of these there will be different shear rates that is happening, correct? So what are the idealized flow, flow, and then what are the complex geometries that are involved, okay? And then phase change, heat transfer and mass transfer that is happening, reaction. So these are some of the aspects when you consider when you have to analyze a polymer processing operation. So these aspects were all discussed in the lecture 69, that is polymer processing operation, sorry, polymer processing 2. Okay, so did you get brief idea on whatever the concepts that were discussed in the week 9 lectures? Okay. Now, can we proceed with the practice assignment session? Okay, you got an idea. Okay. Okay. So, let's go on to the practice assignment questions. So, the first question, this is actually a GATE 2021 question. Okay. A particular free radical polymerization process yields a polymer with a number average degree of polymerization xn bar is equal to 100. The monomer concentration is doubled and the initiator concentration is increased by 4 times. Assuming that all rate coefficients and other parameters remain unchanged, the value for the uh, number average degree of polymerization under the changed condition is, what is the number average degree of polymerization is asked when the monomer concentration is doubled and initiator concentration is increased to 4 times. And the next part of the question is what happens to the rate of polymerization. So these are the two questions. So any idea on how to proceed with this? Okay. So what are the points given? Given it is a free radical polymerization and number average degree of polymerization is 100. Okay. And then what they've given from the initial condition, the new condition is that the monomer concentration is doubled. That means Cm2 is equal to 2 times of Cm1. And similarly, the initiator concentration Ci2 is equal to 4 times of Ci1. Okay. So they have asked what will be the number average degree of polymerization in this case. So the relationship for a free radical polymerization is that your number average polymerization is equal to Kp into rate constant for propagation into concentration of monomer divided by 2 times square root of uh, rate constant for initiation multiplied by rate constant for termination into concentration of the initiator. So from this you can get the relation that your number average degree of polymerization is proportional to Cm, that is concentration of monomer, divided by square root of concentration of your initiator. Correct? So now the next is just mathematics. So it is xn2 bar by xn1 bar. So in case 2, the number averaged the number averaged degree of polymerization to case 1 number average degree of polymerization. So is equal to Cm2 by square root of Ci2 whole divided by Cm1 by square root of Ci1. Right? So they are given what is the relationship between the Cm2 and Cm1 and similarly Ci2 and Ci1. So it is Cm2 is nothing but 2 times of Cm1 divided by Ci2 is nothing but 4 times of Ci1. So square root of 4 Ci1 divided by Cm1 by square root of Ci1. So Cm1 gets cancelled. Square root of Ci1 gets cancelled, and when you take root 4 out of the square root, you will get 2. So 2 by 2 is nothing but 1. So what happens in this case is that when you actually increase the concentration of monomer by 2 times and increase the concentration of the initiator by 4 times, actually your number average degree of polymerization does not change. So your xn2 is equal to xn1, that is equal to 100. Okay. You got it? Now the next part of question is, what happens to the rate of polymerization? Now for the relationship for the rate of polymerization is equal to Kp into Ki by Kt whole power of into square root of Ci into Cm. Okay. Now again you have the relationship. So you can again take ratio of the second condition to the first condition. So Rp2 by Rp1 is equal to square root of Ci2 into Cm2 by square root of Ci1 into Cm1. So square root of Ci2 is square root of 4 Ci1 and square root and Cm2 is 2 times of Cm1. So what happens in this case is that the rate of polymerization in second case is 4 times the rate of polymerization in the first case. Okay. So when the concentration of monomer is doubled and initiator is increased by 4 times, your number averaged degree of polymerization does not change. But your rate of polymerization increases by 4 times. Okay. In case of free radical polymerization. Okay. Now let's go on to next question. So following graph shows the operating window for an extruder. Two speeds of extruder screw rotation, that is RPM1 and RPM2 are being shown. You could see in the figure. So this figure is pressure drop versus flow rate, and your RPM1 and RPM2 are given. That is two rotation speed are given, and similarly two diameters of die are also given, and their characteristic behavior for flow rate versus pressure drop is given. Okay. Now you have to find out whether the diameter of die 2 is greater than diameter of die 1 is greater than diameter of die 2, and RPM 1 is greater than RPM 2, or is it die 1 diameter is greater than die 2 diameter but RPM 1 is less than RPM 2, or is it diameter 1 of die 1 is smaller than diameter of die 2 and RPM 1 is also smaller than RPM 2, or diameter of die 1 is smaller than diameter of die 2, whereas RPM 1 is greater than RPM 2. So how do you find it? Any idea? You have the flow rate versus pressure drop. So how do you find which is having a higher diameter and which RPM is higher? One is higher or two is higher, and one diameter of one is greater or two is greater. How do you find out? You have the pressure drop versus flow rate relationship. Any idea? You can just go through the graph. You need not even go through the lecture to answer this question. If you just find out, you can just find out, interpret from the plot itself. So how do you find out? Okay. Okay. So, for example, when you consider a particular pressure drop, okay, when you just draw a vertical line, from the particular pressure drop, you can see my cursor pointing, right? If you just draw a vertical line for a particular pressure drop, die 1 and die 2. Okay, so die 2 will have a higher flow rate compared to die 1, right? For a particular pressure drop. That means the diameter of die 2 should be bigger. So then only, for the same pressure drop, there will be more flow rate. So more, material flowing through it. Okay, that means diameter of die 2 should be greater than diameter of die 1. Okay. Similarly, for RPM also, if you consider the same pressure drop, RPM 2 is having higher flow rate compared to RPM 1. Correct? Are you able to make it? Yes. That means RPM 2 should be greater than RPM 1. So the answer is Option C. So die 2 should have a greater diameter than die 1, and similarly RPM 2 is greater than RPM 1. Okay. Next question. Identify if the statement is correct. Good wet out and dispersion are essential for composite fabrication. Is it true or false? So the fiber should have a good wetting with the polymer, and it should also be dispersed properly in the polymer. So are these two essential for composite fabrication? Do you think these two are essential for composite fabrication? Manshi, are you there? Is the statement correct? Good wet out and dispersion are essential for composite fabrication. Are you there? Are you able to get it?
Yes, ma'am, I'm here.
Do you think it is required for a composite fabrication? Good wet out and dispersion?
मम नहीं पता.
Huh? I think I'm not able to hear you properly. Can you just type in the chat box? No. Okay, that's okay. It is actually the statement is correct. Okay, so when you have composite fabrication, these are certain parameters that are to be considered. Okay, there should be high strand integrity. Okay, and good run out in continuous process and good wet out and dispersion. That means the polymer should be properly wetting and there should be good interaction between the polymer and the fiber. Okay, and then the fiber should also be properly dispersed in the system. So this is a important aspect in terms of composite fabrication. Okay, now let's proceed to the next question. Okay, in xanthan gum, the extended chain with helical conformation in solid state is due to in xanthan gum. What happens is that in solid state it will have a extended helical conformation. Why is it so? We discussed on different interactions, right? In xanthan gum. So it is due to one of these interactions that in solid state, the xanthan gum will have an extended chain with helical conformation.
Ma'am, I don't have any idea. मैंने actually lectures properly नहीं देख पाई.
Okay, okay. Let me actually proceed with the answer. It is because of the hydrogen bonding. Okay. So this is the actually structure.
Okay, okay.
Okay, this is actually the structure. So you see a lot of OH groups, right? You see a
Yes.
lot of OH groups. So there will be hydrogen and also you have COH group. Okay. So there will be hydrogen bonding that is happening and this leads to a helical and extended chain conformation in case of xanthan gum when it is in solid state. Okay. So intermolecular and intramolecular hydrogen bonding. So this OH group and COH group, they'll have within the molecule also there will be some hydrogen bonds that are being formed that leads to a helical structure and also some intermolecular hydrogen bond that is leading to an extended uh, that leads to this helical extended chain conformation. So because of both of these, you will have an extended helical conformation. Okay. Now let's come to the next question. So consider two plates. Okay. One plate is made up of aluminum. The other plate is made up of stainless steel. They are bonded together by an adhesive. Okay. So what you are going to do is that you are going to pull apart these two. Okay. So let me on maybe. So what you are going to do is that Is my video on? Yeah. So one is steel and the other one is aluminum. So now you're going to pull. So these two are bonded by a adhesive. Now what you're going to do is that you're going to pull apart these two plates. Okay. When you pull apart these two plates, okay, what has happened is that you have the separated plates. In the separated plates, you have certain portion occupied by the adhesive and certain portion of the exposed metal also. Okay. So in this case, what type of failure has happened? When you have some portion of metal being exposed, what type of failure has happened? Okay. So the answer for this is that it is actually the adhesive failure. Okay. When you have an adhesive between two plates, okay, and when you separated and the separated plates, even you would have done this, you would have pasted two materials and you would have just pulled it apart, with the gum you would have pasted and you would have pulled it apart. When you see, in both the surfaces only the gum, then it is a cohesive failure. That is, the gum has actually the interaction between the gum molecules within the gum molecules has actually failed, and that is why, but it has bonded well with the material, for example your metal, very well. Whereas when you have actually when you see the exposed surface of the uh, metal, for example here you are able to see some exposed surface of aluminum, or you are able to see the exposed surface of stainless steel. In this case what happened is that the adhesive has not stick to the portion. Otherwise there will be adhesive, right? You have pulled it apart, there was some adhesive in the middle, you have pulled it apart. If the adhesive has properly stuck to the metal surface, then you will see the entire metal surface filled with the adhesive. The open part will be filled with the adhesive. But the adhesive has not stuck properly in the metal surface. Okay. That means there is a adhesive failure that has happened. Okay. These are two types of failure actually, that occurs in a, when you use a adhesive. Okay. It can be cohesive failure or adhesive failure. When you see only the adhesive on both the surface, it is a cohesive failure. Okay, the adhesive molecule has ripped apart. Whereas when you see, some open metal surface or open wood surface or something, when you have joined some wood and paper and you see some open wood surface, then the adhesive has not actually stuck to the surface properly. Then it is actually a adhesive failure. Okay, you are able
Yes,
to.
ma'am. Got it. Yeah, I
Okay,
got it.
yeah, okay. Now let's go on to next
You
question.
explained it very well,
Okay, fine.
so
Okay,
deeply.
okay, okay. Now let's go on to the next question. In associative thickness, the association is through sticky ends made of dash blocks. So, see, these associative thickness are nothing but your water-based paints. Okay. So, they have some sticky ends. These sticky ends are made up of certain blocks. Okay. That is what it causes the behavior of stickiness. So, this blocks, what is it made up of? Is the question. The answer for this is that these are actually made up of hydrophobic blocks. So if you see the adhesive, water-based paints or adhesive thickener, associative thickeners, classic example is hydrophobically modified ethoxylated urethanes. Okay, if you see the structure, okay, you will see some R2 and R2 here. These are the hydrophobic ends. Okay, these hydrophobic ends, what they will do is that they tend to align. So these hydrophobic ends tends to stick together. That is what you see, these green kind of round segments, they are getting associated, right? So this is what it makes their end sticky and they get associated, and that is how they form bridges, and they form some 3D network. So, and they bridge the polymers, okay, or polymer and another particle. Okay, for example, in the surface, it will bridge, the surface and the polymer particle. Okay, they are hydrophobic ends. Okay, they get associated and they form a 3D network. You are able to understand?
Yes, ma'am.
Okay, now let's go on to the next question. In addition to solvent diffusion, segmental relaxation, disentanglement, the dissolution of semicrystalline polymers also involves. So we saw that in amorphous, polymer dissolution, the polymer solvent has to, the solvent has to diffuse through the polymer, and it has to cause segmental relaxation, and it has to cause disentanglement and all. Right? That was explained, when I was discussing, the dissolution lecture, brief of dissolution lecture, I was explaining, right? Uh, these are, some of the parameters that actually plays a vital role when an amorphous polymer has to be dissolved in a solvent. Okay. Whereas when you come into semicrystalline polymer, in addition to the solvent diffusion, segmental relaxation, and disentanglement, there is additional thing that has to be brought in order to dissolve a semicrystalline polymer into solvent. What does that aspect do you think? What, different in structure does a semicrystalline polymer has in addition to an amorphous polymer? Any thoughts? Because there were a lot of discussion on semicrystalline polymer in previous set of lectures also. What in addition it happens? So there is some crystallinity, right? And this crystallinity is happening through some chain folding, right? The chain starts folding and then they form lamella, right? Do you remember?
I do recall something. Yeah.
Yes, yes, they form lamella and then spherulites and all. So this was discussed. So this chain folding, so they first, the chains start folding and then they form lamella. That is what, the process of crystallization will happen. Okay. So this chain has to unfold. Okay. And then only, it will help, supporting the solvent diffusion, and then segmental relaxation and disentanglement. All these also will happen. Okay. The chain has to also unfold along with solvent diffusion, segmental relaxation, and disentanglement in case of semicrystalline polymer. Okay. The next question is, in suspension polymerization, wide distribution of monomer droplet size leads to dash molar mass distribution. I think since you just heard the brief recap, you wouldn't have idea. Let me discuss the answer also. So it actually, what happens in case of suspension polymerization is that when you have wide distribution of monomer droplet size, it leads to a broader molar mass distribution. Okay. Uh, why is this? Because in suspension polymerization, your monomer molecules are suspended in a solvent. Okay, and each of these monomers, it acts as a reactor. Each of these monomer droplets, it acts as a reactor, and polymerization happens in these droplets, monomer droplets. Okay, and this monomer droplets, it decides, for example, a monomer droplet is of 2 nanometer size means, so that particular droplet will determine the polymer size also. So polymer size, obviously that means it determines the molar mass of that particular piece of polymer. So if you have varying monomer droplet size, for example, you are having varying monomer droplet size from 2 to 100 micrometers. That means your polymer molar mass distribution will also be varying that much. That means you will end up with a broad molar mass distribution. Okay. I hope you got it. You just got some idea of it.
Yes, ma'am. Now I got it.
Okay. Next, melt flow index is directly proportional to molar mass. Is it true or false? For example, okay, let me put the question in a different form. When melt flow index is high, the molar mass, when the molar mass is high, the melt flow index will be high. Is it true? Or when the molar mass is less, the melt flow index is less. Or the other case, when the
When
molar
the when the Malfo index when the molar mass is high, Malfo index will be also high.
will be high.
It's directly yes, yes, it's directly proportional.
So when the molar mass is high, the material flows easily, is it?
Yeah, how much I recall.
Okay, it is actually false. So this is what is the relationship. So so your molar mass, it increases, your melt flow index actually decreases. So if, sorry, So this is your increasing direction of molar mass, the left pointed arrow, whereas your melt flow index is right pointed arrow. So when you have, higher and higher molar mass, what happens is that your melt flow index or the capability of flowing will be very less, because
Reduced,
yes,
reduced.
yes, because
Okay.
as your molar mass increases, there will be more of viscosity buildup, right? So obviously, when there's more viscosity, the flow will be less. Correct?
Now I got it. As molar, because of molar mass increases, its viscosity will also increase, na?
Yes,
And
yes,
due to
yes,
this, the flow will be decreased.
yes,
The rate of flow will be decreased.
yes, yes, yes,
Okay, okay.
yes, yes. Okay. Now next question. The plot shows apparent viscosity versus shear rate for Newtonian, dilatant, and pseudoplastic fluids. Okay. Based on this plot, the fluid behavior as mentioned below, find out the correct combination. Okay. So 1 refers to dilatant fluid, 2 refers to Newtonian fluid, 3 refers to pseudoplastic fluid. Okay. And you have 3 curves. One is curve P, curve Q, and curve R. So which of these corresponds to which type of fluid? The figure, it gives a plot of shear rate versus apparent viscosity. At least one you can.
I will go with D. D. As P is a Newtonian fluid,
Okay.
straight line for Newtonian fluid,
Yeah. Okay.
dilatant fluid will be Q, and for pseudo plastic fluids it will be R. How much I go? Is it so?
So pseudoplastic, you're saying it is R.
Yeah,
Is it
I'm not
so?
sure about it. I'm not sure about it.
Okay, but you're sure of P is
A
Newtonian.
Newtonian fluid, yeah.
Okay, okay. So one answer is right. P is Newtonian fluid because your viscosity is constant with shear rate. Correct? That is what is Newton's law of viscosity, right? Stress is proportional to shear rate, and your
Yes, ma'am.
constant is apparent viscosity, and it is constant for a Newtonian fluid, right? And so, as you said, it is P is Newtonian fluid, whereas your Q is actually pseudoplastic. It is actually a shear thinning fluid. Okay, pseudoplastic fluids are nothing but your shear thinning fluid. With the application of shear, the viscosity decreases. Okay, and your R is your dilatant fluid. With application of shear, your viscosity increases. Okay, and this is what is the relationship when you have of your shear rate versus your shear stress for these fluids. For Newtonian fluids, it is a linear relationship, right? Whereas for a here again, your pseudoplastic fluid is Q. Your shear rate actually, sorry, with increase in shear rate, there is also a decrease. Whereas in case of your dilatant fluid, there is an increase in shear stress. And in case of Bingham plastic, it again gives a linear relationship, but it needs some yield stress. Okay, beyond a certain point only, it will start flowing. Your Bingham plastic. Okay.
Yes, Bingham glasses is P and Q for pseudo and
Uh,
dilatant. Okay,
yeah.
okay.
Okay. Next is in injection molding, high holding pressure. So if the holding pressure is very high, what does it leads to? It actually
Back
leads,
backflow, backflow,
huh?
backflow हो जाएगा. Nozzle block हो जाता है.
Nozzle block you're saying.
Yeah, due to
Okay.
which it will backflow. Material will flow back.
Backflow, okay. Nozzle block and backflow. Okay. Okay. What happens is that it is actually mold overflow will happen. So the mold may not be perfectly shaped. So it may have some small openings or something. So through which, due to very high pressure, there will be some leakage or flashing out of the polymer melt. Okay, this is
So
what
it's
is the
asking for high holding pressure. So holding pressure is for what? In
holding pressure of
injection
the
molding,
polymer melt. Holding pressure of the mold.
barrel, the material feed in barrel. It's all about for the material feed in barrel. High
Yeah,
holding
yes, yes.
pressure.
Yes, see, I didn't get your question. Can you just repeat it?
जो हाई होल्ड प्रेशर है वो किस पॉइंट के लिए बात कर रहे हैं हम? बैरल में जो मटेरियल फिल्ड है उसमें या इंजेक्शन प्रेशर की बात कर रहे हैं या किस चीज की?
No, when you are doing the injection molding, you apply a
फिलिंग
you apply
फिलिंग
a
द मोल्ड.
pressure, right? Your mold, the molten is pressurized and then it is passed through the mold. So when this holding pressure inside the mold is very high, okay, when it enters the mold, when the holding pressure is very high inside the mold, so this is what is your mold. You could see your mold, right? This portion is your mold. So when your polymer melt is held up in this mold, okay, during the injection molding process. And when this holding pressure, to hold in the mold, there should be some pressure, right? Because you could see some small uh, complex shape in the mold, right? So when you have very high holding pressure, what happens is that there may be a flashing out or overflow. Okay,
ओके ओके.
you're able to get it when it and when it enters the mold, when the holding pressure is very high. Okay,
यस मैम, गॉट इट.
yeah.
या.
The final question is, Weisenberg number is given by Weisenberg number is a dimensionless number and it is very important in terms of polymer processing. So what is, how do you define this Weisenberg number? Any idea?
नो मैम.
Okay. So Weisenberg number, it is given by your velocity over length multiplied by your characteristic relaxation time of the polymer. It is actually your strain rate multiplied by your relaxation time of the polymer, or it is, in other words, you could say that the time scale of strain rate, that is gamma dot, into your material relaxation time. Okay, because in processing operation, obviously you play with different strain rates, right? You're straining the polymer to different extent, right? So that strain rate time scale multiplied by your material time scale is what is your Weisenberg's number. Okay.
ओके 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 मैम.
Okay. That's all with the session.
आई एम थैंकफुल टू यू मैम. आई एम थैंकफुल टू यू.
Okay, that's all with the session. Do you have any other doubts?
अबाउट एनपीटीएल एग्जाम व्हेन इट हेल्ड ऑन अक्टूबर में है पेपर
Yeah,
तो.
I think it is in
तो
October. That is what.
yeah, that will be on the like centers.
Yeah, it must be in the centers, I guess.
Okay, okay. And